everyone. This is our first seminar in spring 2021 semester, and every week from now until sometimes in April we will have weekly seminars. So make sure that you attend and make sure you sign in a few minutes earlier in advance. Also, please make sure that you stay to the end of the seminar. So this is our first seminar again. It's a great pleasure for me to introduce our speaker, Dr. Hosseinzadeh. So he's going to be basically talking about additive manufacturing. And this semester, we try to have a variety of different topics. So, hopefully you guys will all benefit from the seminars in different weeks. So today's seminar is going to be about computational manufacturing and cyber-enabled design in metal additive manufacturing to accelerate innovation. Our speaker has a long history and background in 3D printing and manufacturing with a PhD in material science, and he's a visiting scholar at the University of Wisconsin, Madison. With that, I'll turn over to our speaker, and the floor is yours.
Thank you so much. Thank you so much, Sujidi. It's my pleasure to have a presentation about computational manufacturing, and I hope that you can use my presentation. I hope that this presentation is useful for you. The title of this presentation is Computational Manufacturing and Cyber-Enabled Design in Metal Additive Manufacturing to Accelerate Innovation. This is my background is I have a PhD in material science and engineering. In 2019, I started a project on manufacturing technology, and I'm developing computational code and software with the focus on additive manufacturing. The first product is Complex software, which is a beta version. It is not commercial and it's free for everyone, just for academic activity. And this product is a computational facility for process modeling of metal 3D printing. I always like to talk about some other. These are my favorite scientists, like Richard Feynman and Leonardo da Vinci, and I'm inspiring from them. So this is part of my character. I like to read their books and their papers and follow them in their academic life. This presentation has 5 chapters. I want to talk about some general aspects of computational manufacturing. I don't want to go to some mathematical details, but if you have any question about the details, I will be more than happy to interact with each of you by email. We can share some documents, we can interact with them, but in this presentation, I will go through general aspects of the mathematics and computational methods. First, we have an introduction. Second, we discuss about computational engineering. Then we will focus on computational metal additive manufacturing. And at the end, I will talk about cyber-enabled design, which is very new. We do not have a published paper in this field yet, and we do not have any available technology. So it's kind of futuristic term, and we will need to talk about it. At the end, it looks like a Hollywood version of cyber-enabled. So we will discuss about it. It looks like fun. So we have 5 sections. The first section, I'm sure that most of you are familiar with additive manufacturing because it's a polymer version of that. It's almost cheap and available for everyone. So I will not talk about additive manufacturing, but about the metal additive manufacturing. It's a little more complex because we need to have a local melting and add metals layer by layer. So the process is a little complex, and it's recently metal 3D printing became popular, and it's a promising method for complex shape. And I'm sure that you are familiar. Just these are some general topics. We have two kinds of metal additive manufacturing: powder bed fusion and directed energy deposition. Recently, scientists focused on microstructure and mechanical properties of 3D printed samples. To discuss about the microstructure and mechanical properties, we need to have information about the thermal history and melting and solidification condition during 3D printing. It's not easy to put a thermal sensor in the during metal 3D printing, so simulation could help us a lot in this field, and it's a benefit of simulation for metal 3D printing. And also, we need to have information about the final mechanical properties of the printed sample. These are the general topics and important topics of the metal 3D printing. And scientists are working to optimize metal 3D printing process for commercial application. The system we have commercial 3D printers, but metal 3D printers, but we still need to work to optimize the whole process. Because the metal 3D printing is a complex process, and we have anisotropic material properties, innovation and improvement is difficult and expensive in this field. So we need to find a way to accelerate. So I think that it is enough to talk about metal 3D printing, because I'm sure that you are more familiar than me in this field. But about the innovation, in advanced countries like United States, the time from invention in the lab to have a commercialized product, as an average, we need 18 years. Do you have any examples that we have more than this time, or have the product can go to the market less than 18 years? But as an average, this an average time. If you have an idea, if you have a prototype of it in your lab, if you want to make it commercial, as an average, it takes 18 years. You need to find a way to accelerate this process. So the question here is, how can we accelerate the innovation, invention and idea to market in metal additive manufacturing? I will discuss about this and answer this at the end of this presentation, but please keep in your mind this question. So we discussed about the complexity of the whole process of metal additive manufacturing, and we know that computational method could help us to understand the thermal history and mechanical residual stress and thermal stress, residual stress in the whole process, which is not easy to experimental validation or something like that in this field. So simulation could help us a lot. Okay, so we have some terms in simulation. One of the terms is ad hoc simulation, ad hoc research. As a general, we have three approaches: experimental method, computer simulation, or an analytical method. You are all familiar with these three concepts. And experimental methods are based, and then based on the experimental method, we develop some analytical model And when we have a well defined analytical models and some database, experimental database, we can run computer simulation. And we can use computer simulation to give some information and idea for developing experimental test or analytical model. So this is a circle. They are helping each other. But in most cases, we are using each of these approach or all of them together for ad hoc simulation. What is ad hoc research? What is ad hoc research? Ad hoc research is research that is designed to address a particular problem or issue. For example, we use these approaches to understand the effect of scan speed or laser power on final distortion in the printed sample. This is an ad hoc research. Okay, so sorry, I have a problem with this. Okay, so when our approach is ad hoc, our focus is on a problem. So this is not a fast method to optimize the whole system, to optimize the whole process of metal additive manufacturing. Okay, so, and also I need to add another point that mathematical model has, mathematical models have several hundred years ages, but computer simulation is very young. The age of computer simulation is less than half a century. And we need to develop the concepts of computational techniques and maybe numerical method, everything, but it's very young. If you want to compare computer simulation to analytical model and experimental model, computer simulation is very, very young. Okay, so if you want to run ad hoc simulation and focus on a project, maybe we can develop a simple computer simulation. But sometimes we need to simulate the whole process, and we want to have many parameters, consider many parameters in our system. We need to use multi-scale, multi-physics simulation technique, consider different scales from quantum to mesoscale, atomistic to mesoscale, and to macroscale. In this case, our simulation is not ad hoc, and also we use another term such as integrated computational engineering. So this is integrated computational engineering, or other name like this, integrated computational material engineering. They are all almost a relatively new discipline, and their focus is to solve complex physical systems. This is a good approach for metal additive manufacturing, because metal additive manufacturing is a multi-scale, multi-physics, and complex system. For example, if you have a tensile test, you apply load on a sample. That's a simple simulation, and this is not multi-scale simulation. But metal 3D printing is a complex process, and we need to consider many variables. So we need to consider the complex system. So we need to use integrated computational engineering, and also maybe we need to go beyond ad hoc simulation. So what do we have? What kind of computational technology what kind of computational technology do we have now, and how can we use them? If you look at this graph, it's a very nice graph for uh, computational material and mechanics. We have velocity and mass, and if in the graph you can see you can divide quantum and classic relativistic and non-relativistic systems according to the size of the system and the velocity of the system. For metal additive manufacturing, we are in the domain and region of Newtonian mechanics, which is classical and non-relativistic. And maybe, for some cases, we need to go to atomic scale. For example, if you want to simulate the nucleation in the melt pool, nucleation, the solidification and nucleation of solid metal from the molten metal in the melt pool, we need to use quantum simulation. So we need to use Schrödinger equation and solve quantum simulation for that. So mainly we need Newtonian mechanics. Sometimes we should use quantum simulation as well. But so you can see that for computational metal additive manufacturing, we are in the quantum and classical non-relativistic simulation. So, and we need to check what do we have now. For Newtonian mechanics, we have conservative equations and constitutive equations. Constitutive equations are some famous equations like Fick's equation, Hooke's law, heat diffusion equation, which are developed by fitting a graph to experimental result or something like that. But conservative equations are the general concepts of balance of energy. We have three equations: mass, momentum, and energy. Mass and momentum are vectors, so each of them is three equations, and energy is a magnitude, so it's just one equation. Conservative equations are 7 equations. The general form, there are 3, but because we have x and y direction for equation 1 and 2, at last we have 7 equations. Equation 1 is a continuity equation. We can discuss about it later, but for the momentum, I think that this is a very important equation. From this, we can calculate stress strain, deformation of the system, and internal stress in the system. If we expand the equation, we have 3 equations in x and y direction, and z direction, and then you can see the details. And also, if we colorate the shear force to the viscosity by some assumptions, we can see here we can change this formula for fluid dynamics. If we use a constant viscosity concept and non-compressive fluid, which means that we have constant density, this would be a Navier-Stokes equation. So you can see that. So you can use a momentum equation for solid and also for liquid. The last equation, which is energy equation, if we simplify it, we can calculate the temperature. So we have, for metal 3D printing, if you want to calculate the thermal stress or residual stress, you need to use this form of momentum equation. If you want to simulate the melt pool, we need to use Navier-Stokes equation, but because we have a free surface, we need to add some other method. For example, volume of liquid or other methods to capture movement of the surface of the melt pool, but this Navier stock some assumption is working very well for metal additive manufacturing, and also for um, thermal history, we need this equation. They are very commonplace and simple to use. For the mesoscale, we need if you want to if you want to simulate a microstructure, we need to go to mesoscale, and we have many methods, but standard methods are discrete one and continuous one. Discrete ones like Monte Carlo and cellular atometer, and they have probability. They are stochastic concept. They have stochastic concept. The phase field is a continuous method. You can see the equation of that. We have an order parameter, and we develop the energy of the system based on the value of the order parameter and the slope of the order parameter. We define the energy of the system and put in the equation, time-dependent equation. You can see that. So we minimize the energy for the order parameter, and we can capture the movement of the order parameter. Order parameter is working as interface in this. So, for example, if you have a grain, polygrain system, you want to see the grain growth. The order parameter is the grain boundary of the system. And also, we have computational thermodynamic methods such as CalFOT for predicting, for example, the binary phase diagram. And based on that, and if we have a cooling curve, we can predict the microstructure based on computational thermodynamics. So these are the three main mesoscale methods for predicting the microstructure. We need to solve all the equations. So we need to use numerical methods. We have several famous numerical methods: finite element, finite difference, mesh-free, finite element discrete method, time domain finite difference method. If someone asks me which one is more accurate, I would say that all of them are good for the simulation, and it's up to you to select which one is better for you, and the accuracy of all of them is enough for most of engineering applications. But according to the system, sometimes we need to use finite elements, sometimes we need to use finite difference, sometimes it depends to the system. We should discuss based on the physical system. Okay, so these are the general concepts and the computational technology that we have. Now, I want to focus on computational metal additive manufacturing. What we want from simulation in metal additive manufacturing. Okay, so before moving forward, I want to be sure that could you hear me? Could you see me? Or if there is any problem, please let me know. Or if you have any questions, I could do that.
Yes, I have been hearing, and it's a little bit noise still, but I guess it's good. And thanks for the pause. We're gonna basically go to the question at the end, but if anyone has a question right now, please put it in the chat box, and I'll basically take a look.
Okay.
Thank you.
So I will continue now. If you have any question, I will see. Okay. So what do we want from computational metal additive manufacturing? We want to simulate thermal and mechanical response of the material during and after processing, the evolution of the material's microstructure during the processing, the mechanical properties, representing the material that results from the development of the final microstructure. So we want to simulate thermal history and mechanical response such as residual stress and deformation. We want to take and simulate the final microstructure, and we want to see what is the mechanical properties of the printed sample, local mechanical properties. Another important subject is the defect. Current simulation technique and the computational method that I explained in previous slide could not simulate accurately the defects. Some kinds of defects in the melt pool could be predicted by simulation if we use fluid dynamic simulation, but they're very, very limited to one or two layers. We cannot extend it to the whole sample because if we want to use fluid dynamics with the resolution at the metal powder and capture one track of spindle layer, for example, in SLM method, and use surface method to capture the formation of the surface of the liquid. And it takes just very several centimeters, one layer. It needs 2 or 3 days to simulate it. So this is not simple to simulate the whole sample, large sample, and check all the defects. But we can use some analytical methods or some other techniques to predict this. But simulation is not as strong in predicting defects in comparison prediction of thermal and mechanical and microstructure. So we need to work on this part. As we discussed in computational, in metal additive manufacturing, we have two techniques. One, laser deposition. The other one is selective laser melting. I'm talking about laser. We can change the heat source, but in this presentation, I'll just talk about the laser. Let me talk about some details about these two methods. Laser power of SLM is in the range of 200 to 400 watts. Laser power of the DLD is 500 watt to 10 kilowatts. So you can see that the laser power in DLD is much larger than SLM. The other thing is the laser diameter. Laser diameter is around 100 micrometer in SLM, and in DLD method, it's around 1,000 micrometer. So you can see that because of this, we have two different lengths scale of simulation. If we want to capture the thermal simulation in SLM, we need to have mesh size lower than the diameter, laser diameter. So the mesh size in SLM method is much lower than DLD. The other thing is the speed, scan speed. Scan speed in SLM is several hundred millimeter per second, but in DLD is just several millimeter per second, maybe 1 or 2 millimeter per second. So the heat input in DLD is much larger than SLM. Because of these parameters, example parameters, the simulation method of SLM and DLD is not the same. We need to use a different assumption, different computational methods and techniques to simulate each of them. They are completely different. So I need to discuss each of them separately. First, I want to start talking about DLD. First, we can first important subject in the DLD method is how we can update the simulation domain during each time step. Uh, because we have molten metal received from printer nozzle, and we need to add this new molten metal during each time step to the simulation domain. This is very, very challenging if you want to consider it as a liquid, as a molten metal, and use fluid dynamics. We are limited to a very small part of the sample, and we need a huge amount of CPU time. So if you want to print a larger sample to see what is the total deformation in the sample, definitely we need to use another technique. I need to be honest with you, the only method for capturing, for simulating metal, DLD method for the large sample is birth and death element method, or birth element method, which means that we discretize a large sample, but kill most of the elements. The value of the element is 0, so they are not involving in the simulation. When we need them, we active them. This is the only method that we have right now for the simulation of for the large of the large sample. You can see in the graph we have blue and we have blue and yellow cubes and boxes. So one of them is melted, the other one is solidified. And the melted one is just received from the nozzle, and the solidified is the old layer, which is solidified now. So step by step, we add the melted one on the previous one. So at the end, we have a printed wall. So you can see that step 1 to step 7, how we add new element. Consider each box as a computational element. So at the beginning, we discretize the whole system, but all the elements are dead. In step 1, we active just 4 elements which are yellow. You can see that in step 1, we just active 4 of them. In step 2, we have blue boxes which are solidified now and active, and we active 4 new elements according to the movement of the nozzle, and so on. This is the only way. We don't have another computational technique yet. This is algorithm, general algorithms. I don't want to go through the details. You can take the reference, publish one about that. So what we can get from this simulation? We can add some computational sensors and extract thermal history, mechanical history, and microstructure for that computational sensors. For example, in this figure, we have 4 layers printed on each other with DLD method. And we have 3 sensors, A, B, and C. You can see the distance of each point from the top of the first printed layer. And if you check the graph, you can see we have different scan speed, 2, 4, and 6 millimeter per second. And you can see the difference between each layer. because I don't want to discuss about the effect of scan speed, I just want to show you the capability of the simulation. I will not go through the details. And also, if we change the laser power, we can see for these are all for one sensors, and from that sensor we change laser power, and we keep constant the scan speed. So you can see that if we increase the power, what would happen for windmissus stress and also the temperature. If we increase the laser power, you can see we have a higher level of temperature and also stress in the sample. We can take the rate of powder feeding. So if we increase the rate of powder feeding, it means that we have more heating food, and so you can see that we have higher level of stress in the sample. As a general, it is computational method, which is the only one for the large sample right now, and we can simulate the process of DLD method, and we can check the effect of different variables for our sample to see what would happen for the total distortion, residual stress if we change scan speed, laser power, and so on. So we can simulate the whole process. Because we can calculate the thermal history, cooling and heating and cooling curve for each point in the sample, we can run mesoscale simulation, one of the Monte Carlo, cellular automata, hot model, or continuous ones such as phase field, and predict the local microstructure, grain structure, to see if it is equiax or not, if it is columnar or not. And if you look at one of them, for example, for point A, we have cooling curve of point A, and after each peak, we can simulate the microstructure. These are stochastic simulation with cellular atomic. You can see after first peak and second peak, we have a columnar structure, and at the end, we have new nucleated austenites or phase or grain. This is a steel because I said austenite. New grains, and then they grow in the columnar structure, and at the end we have equiax grain structure. It's a green scale from green to black, and each color means a grain. You can see for point A, point B, and point C, at the end, we have different grain size. So if you repeat this for different critical points in the sample, we can prepare a map of the microstructure of our sample. So if we have a complex structure, we can add some computational sensors at different sections and extract the heating cooling curve and calculate the final microstructure for that point and see if it is what we want or not. Or for example, if it is not, what would happen if we change the scan speed or laser power? Can we revise it or not? And you can see in this graph, if we increase the scan speed, the final grain size is finer. If you want to have a finer microstructure, in this case, we need to increase. This is one of the variable that we can change to optimize the microstructure. We can increase the scan speed. Okay, so what I want to say, I want to talk about the capability of simulation in metal additive manufacturing. So we have computational facilities. we can use this to optimize the print parameter to get the final microstructure that we want. Okay, all the simulations done by my personal codes. We have another codes. You are familiar, so it's not advertised. One is ANSYS. Everyone knows this software. We have two other softwares. I don't want to give you the name. If you want, please email me. I will share all the information about the softwares. But in the market, we have software that calculate the melt pool shape during metal additive manufacturing accurately, SLM and DLD, both of them. But at the powder size, you can see left and top here. This is the only one that use fluid dynamics, computational fluid dynamics to simulate the pool shape. Other software are using other techniques. They are using very they are using massive assumptions. So I don't want to talk about that right now because it's up to them about their technique. But we have several softwares you can search and use one of them for your simulations. For the SLM, I told you that the computational method for SLM and DLD is different because of the length scale, the physical length scale of these two methods. Let me show you a video. This is a computational. We have a small cube. We want to print it with SLM. See what would happen. Okay, if the laser moves, and you can see how we can print it with simulation. Okay, so again, in SLM like DLD, we need to find a method to simulate the local melting because we have moving and we have a moving melt pool, so we need to capture. This one is more simple than DLD because it moves in the plane. So you can see step 1, step 2, and step 3. It's very simple, and you're familiar with the function for the laser and the boundary conditions, so I will not go through that. Again, this is another algorithm. This is unpublished research paper, but when published, you can see this. With computational method in SLM, we can add some computational sensors. So again, like DLD, we can simulate the heating and cooling curve. You saw the video, it's the captures from different times. You can see the movement of the melt pool by moving the laser. And finally, you can see the printed tube. So at the end, simulation can help us to simulate the thermal history and the mechanical properties, final deformation. Also, like DLD, we can simulate the microstructure. This one is easier to simulate the whole cross section, not just a very small part like DLD, because SLM, the laser is moving very fast. So the time scale is almost in less than millisecond. So it's almost comparable to solidification time scale. So we can simulate the microstructure for a larger cross-section in comparison to DLD. And because I told you that because of the different nature of these two processes, we have some limitations and we have some benefits. This is a benefit in SLM. If you look at, we have two cross sections. Each cross section has a different print pattern, and at the end, you can see the final microstructure. And this is unpublished paper, but the results, I think that's nice to share. And this is, if you want to compare with the experiment, you can see the simulation can predict the microstructure. Also, if you look at the blue graph, which is a simulated print pattern, a small pattern, I don't know what is the name. We have the same black line in the metallography image, which is the line at the end of the melt pool. The simulation can also predict that. You can see. So in the SLM, again, we can we have enough computational methods, and they are accurate almost to simulate thermal history, mechanical properties, deformation, and also microstructure. This is another video. I think that is easy to share. In this video, you can see the microstructure during solidification. I told you that because the laser is moving fast, the time scale of solidification and the laser movement is almost the same, so we can capture it. So you can see that it is the grain structure, the gray scale is differentiating between each grain. So the color, the meaning of the color is a grain. Okay, so I talked about computational method. We are using conservative equations for energy, momentum, and mass to simulate at macro scale the thermal history and the mechanical properties and residual stress and deformation. For them, and we can couple the macro scale computational method with one of the mesoscale simulation technique. We have some limitations. I told you that if you want to print a large sample, we could not use fluid dynamics because we need a large CPU time. But if we use many assumptions, like the assumptions that I explained, using burst element, dead and burst element, or burst and dead elements technique, we can print a larger sample. And at the end, we can run ad hoc simulation or a process modeling. Process modeling is one level after ad hoc simulation. Process modeling, in the process modeling, we will consider several effects of several parameters on the quality of the final printed sample. So this process modeling is kind of several ad hoc simulation. Okay, so I talked about computational metal additive manufacturing. I will be more than happy if you want to some more details about the mathematical aspects of the methods, or some references. If you want to know about the software, please email me. I will back to you as soon as possible with documents and information. Okay, so please let me back to our first question: how we can accelerate innovation. How we can go beyond ad hoc simulation and optimize metal 3D printing process faster. And also how we can add innovations. What I mean, for example, what would happen if we have additional torch, thermal torch, before or after laser nozzle for printing to pre or post heat treatment? Or what would happen if we change the temperature of the chamber? What would happen if we preheat the bed of the system? What would happen if, for example, use several nozzles for the printing? What would happen if we change some parameters? So if you want to, it's not easy and it's not cheap to use experimental method or test all of these with the experimental methods. Or if you want to technically develop the printer to check what would happen if we add additional torch before or after the laser, but we can easily use simulation and do that. But this is also an ad hoc simulation. You understand the effect of one parameter. So if we need to check if there is another approach or not. The answer is yes. We have another approach, which is cyber-enabled design. What is cyber? Cyber is, this is exactly the meaning of this figure. We have many scientists, experimental, computational scientists around the world working on many ad hoc simulations, many ad hoc experimental cases. And they are working, one of them working on steel, the other one working on other alloys and functionally graded materials. So if we could connect all of them together and use all the information in one platform to make a better decision. And this is the cyber approach. So what is the cyber? If we could use computational algorithms and simulation methods and infuse computational algorithm and simulation method in a massive experimental and computational database by eliminating the geographic constraint for collaboration and experiment. This is the cyber-enabled approach. Then we can accelerate method discovery and innovation and process optimization and control. As a summary, for the cyber-enabled design, we need a software for integrated computational engineering. In the cyber-enabled, this is a computational brain. Also, we need a computational big data, experimental big data, and internet to connect all of them together. This is a cyber-enabled design. So we need to have experimental database, computational database, and computational brain. So far, we do not have this platform of all these three databases and brain, computational brain. We need to work to develop this. I want to show you some Hollywood version of that. If you could do that, it would be something like this. Your family, you all saw this. It's a computer that Tony Stark talked to the computer to design a material and final exoskeleton, his exoskeleton. And you can see that this is, if you could do that, this is. This is what is a cyber-enabled. But do we have an example right now for the experimental database? I don't know. I couldn't find. But for computational database, it's about almost 10 years that some scientists working on material genome project. They are working high throughput computational methods to prepare a database for some applications. For computational brain, I don't know, but I couldn't find. And I think that maybe because of industrial version 4, maybe someone wants to work, but at this time, I'm not so sure that we have some publication on this topic. So if we combine cyber-enabled with a high level of AI, artificial intelligence, at the end, we would have Tony Stark computer. It's just for fun. I'm sure that if someone asked me, do we have computational technology to make for making Tony Stark computer for Iron Man? My answer is big no. Our computational method, numerical method, even finite element or whatever, they are not accurate enough for that technology. They are not fast enough, and they are not advanced enough for that technology at this time. So with the current technology that we have, I believe we could not design a computational brain that looks like this computer in the Hollywood movie. We need to extend it. I want to stop at this time, and I'm sorry if I passed the deadline, but I should say thank you for your patience, and if you have any questions, I will be more than happy to answer.
Thank you very much. I put your email in the chat box, so if others have questions, they can basically send it to you later. Thanks again, Dr. Hosseinzadeh, for the presentation. I've got a question. Please put your questions in the chat, in the Q&A, if possible. So I think Pranit, if I pronounce correctly, he has a question. He thank you for the presentation, and at the same time, he's asking about the simulation. Are the simulations performed assuming that the metal additive manufacturing would be isotropic?
I need to ask, what do you mean isotropic? You mean the material properties is isotropic, or the final properties is isotropic? I couldn't get.
Pranit doesn't have microphone, so if you can type it, that would be easier. A materials property, that's basic.
Okay. The input material properties in our simulation is temperature dependent. This is the only anisotropy. But if you mean that in the direction, for example, in this plane or this crystal plane, for this simulation, we didn't add it. But it is very easy to add it. If necessary for the fundamental research, we can add it. But it is for input material. If you mean that the output material properties of the printed sample, yes, simulation could predict it. Predict that. I mean, if you predict the microstructure, you can see the anisotropy in the microstructure, so you can see different material properties in different directions, and simulation could predict it.
So I guess if you guys put your questions in the Q&A, that would be a lot easier to. Corey Williams, Corey has a question. So, so did you add your own methods for the ANSYS simulation? Did you add your own methods to do it, or was it built into the ANSYS already?
According to my understanding, the question want to ask, did I write a module in ANSYS or use ANSYS or something like that? My simulation is I use AM Complex software that I developed myself from A to Z. So this is a standalone code. I didn't use ANSYS or other software.
Corey, is that what you were trying to ask? If no, just put a follow-up here. So, any other question or comments? So I guess yeah, I thought I saw an ANSYS image earlier. Okay, that's confusion here. So I guess Hussein Abedi, he has a question too. So, and sorry guys, because of the time, I'm just gonna read your questions if that's okay. And the issue we have. So Hamid is Hussein is thanking you for the presentation. And the question is that you have the simulation thermal and microstructural modeling. What is the next to be added to make it more complex?
I couldn't hear you. I couldn't hear your last sentence.
Right.
Could you please repeat it?
If you hold it to the mute, because apparently when we both speak, there is a problem. So if you hold it to the mute, you will probably hear better. So the question Hussein was asking was related to the simulation. So he's saying that you have the simulations that thermal and microstructural modeling is done, right? So what are the next steps to be added to make it more complete?
Okay, so the first step is we need to use develop computational method, efficient computational method, because for very small part of the sample, we need to run more than 20 hours simulation. So simulation needs huge amount of CPU time. We need to use and develop good assumptions to reduce the computational time. This is the first step. At this time, we have the code, and it would be good to work to add more accurate assumptions to simplify the system and reduce the time of simulation. This is one section. The other thing is we need to improve the physics. For example, if we could add the meaning of the crystal structure to the microstructure, if we could capture evaporation during the printing because of the temperature of the laser, we need to improve the physics, but we should do this step by step. I think that we are at the earliest stage, although we can simulate the microstructure, but we need to improve assumptions, use better assumptions to reduce the time of simulation, and also enhance the physical meaning of the simulation. So we are in the beginning.
Thank you. Hussein, if you have a follow-up question, please put it in the chat box or a comment regarding your question. And again, sorry, this is the first time. Okay, well, I guess he's satisfied with your answer. First time, so we had a little bit technical difficulties in the noise. So this seminar is basically recorded. Again, if you have any question, the presenter's email I just added over there, and I'm gonna basically have the follow-up question, and that would be, I guess, our last. If you have further questions, communicate to the speaker directly. So Hussein is asking again. So far, we are from predicting the performance of the material, I guess. Is that basically like he's trying to see how far is it that we are from predicting the performance of a given material. You're mute.
Can you hear me now? Okay, I'm sorry for that. If you want to use simulation, print a sample, and see what is the final mechanical properties of the printed sample, we need to use simulation to predict the microstructure. And this is just the topology of the microstructure. We need to use the computational thermodynamics and binary phase diagram to predict the microstructure, and use some analytic method to connect the predicted microstructure, grain structure, and predicted microstructure by thermodynamics by using analytical method to mechanical properties. We do not have any numerical method to straightforward report the mechanical properties of the printed sample. So after simulation, we need to add thermodynamic prediction and then use some analytical model. This is a huge assumption, and I think that this is almost accurate. So I don't know if we could develop some analytical method by using experimental databases. I don't know, database, I don't know. But at this time, we are weak in this field. Although we can do something, but we are weak. We need to do more and more.
Well, thank you very much. Thanks. And given the time, we passed 10 minutes over 2 o'clock. So we started late as well. I would like to thank you again. I really appreciate giving this presentation and willing to be in touch with us. Everyone is basically thanking you, and hopefully we get the chance to meet you in person at some point.
Thank you so much. Thank you for this seminar. I hope that my presentation was useful for you.
Definitely. Thank you.
Thank you so much.
Great afternoon. Bye.
Bye.